Hello, this is the second of two videos talking about molecular geometries, molecular shapes. And we're looking at VSEPR, valence shell electron pair repulsion theory. It says that electron pairs or electron domains around a central atom arrange themselves so as to maximize the angles between them in order to minimize the repulsive forces. And so we've been talking about electron domains. And all the following are a single electron domain. A non-bonding pair of electrons, or a lone pair, they're a single domain. A single bond is a single domain. A double bond is a single domain. And a triple bond is a single electron domain. So each one of those is just a single electron domain. So to determine these electron domain geometries, you count up the number of electron domains around the central atom. Thus far in the previous video, we've looked at 2, 3, and 4 electron domains around the central atom. What we want to do in this video is look at 5 and 6 electron domains. So let's look at the molecule phosphorus pentachloride. And if we were to look at its Lewis structure, it would look something like this. Where phosphorus does not obey the octet rule, it's actually an exception to the octet rule. I mean, there are 10 electrons around that central phosphorus. And when we're doing all these, we're focusing in on that central atom and how the electron domains are arranged around it. Another point to keep in mind is that we can draw a legitimate Lewis structure, but it may not adequately describe the shape of the electron domains or the molecular shape. So don't let the way the Lewis structure is drawn throw you off. The important thing is that there are 5 single bonds to the phosphorus, 5 electron domains. And so I want to redraw this slightly in that these atoms are not all in the same plane. They're not all, it's not a two-dimensional molecule. It actually fills up 3 dimensions. So I'm going to have my phosphorus in the middle. And I want to construct this so that there are 3 chlorines that if we were to think of the phosphorus as being a globe in the center of the globe, that would be on the equator, 3 chlorines on the equator, and 2 chlorines at the poles or along the axis. We don't care about those non-bonding pairs on the chlorines, those peripheral atoms, but these 3 chlorines all lie in the same plane. And these are what we're going to refer to as being in equatorial positions. And those bond angles are 120 degrees. Whereas the axial chlorines, we look at the bond angle between them and the equatorial chlorines, those are right angles. Those are 90 degrees. And so here's my 5 electron domain geometry. And there you can, looking down from the top, you can see these 3 angles. So this molecule is going to be a trigonal type of molecule. If I turn it on its side, and if you can use your virtual reality minds, there's a side, there's a side, and there's a side. I've got 2 3-sided pyramids that are base to base. The bases are touching one another. And so this is a trigonal bipyramid, is the name of the geometric figure. bipyramidal. The trigonal bipyramid, or a trigonal bipyramidal shape. And so there's my top pyramid, and down below's the other pyramid that has three sides to it. It says trigonal bipyramidal. That's both the electron geometry and the molecular geometry, or molecular shape. They're the same because there are no non-bonding pairs on that central atom. So that's my trigonal bipyramid. I invite you to look in your textbook at a picture of it. SF4, sulfur tetrafluoride. Its Lewis structure could be drawn like so. There are 5 electron domains around the sulfur. There are single bonds to the 4 fluorines, and then there's a non-bonding or lone pair on the sulfur. So the magic number is 5 electron domains. That means this electron geometry is trigonal bipyramidal. And so we need to figure out where that non-bonding pairs of electrons is going to go. And so if I redraw this to try to show these axial positions again, and then this being my equatorial position, these 2 fluorines, and there's the non-bonding pair of electrons also on the equatorial position. That's where we find the non-bonding pairs of electrons for any case where we do 5 electron domains. There's an equatorial position, because there the angle of interactions are either 120 degrees with the other equatorial positions or 90 degrees with the axial position. Whereas if the non-bonding pair were on the axial position, all the interactions then become 90 degrees. And so we're going to maximize those angles in order to minimize repulsive forces. So there's my trigonal bipyramid. I'm going to pull off one of my bonds. And so I'm looking down the axis in this position. And so that's where my non-bonding pair of electrons is. These are the 2 equatorial positions. There's an axial fluorine. There's an axial fluorine. And so I'm going to put this down on the surface. And what is the molecular shape? It's called a seesaw. So can you see the seesaw? In this arrangement, there are my axial positions. I've turned this globe on its side. These are my 2 equatorial positions. And now I can rock it up and down. The equatorial positions are the legs on my seesaw, if you will, and the 2 little kids in the playground are on the axial positions. So this is a trigonal bipyramidal electron geometry and a seesaw molecular geometry or shape. So that's the case where you've got a central atom with 4 bonding electron domains and a single non-bonding domain. 5 electron domains in all. Let's look at chlorine trifluoride. Chlorine's going to be my central atom. I've got 3 fluorines. I've got a pair of non-bonding pairs. So I've still got my 5 electron domains. 1, 2, 3 single bonds. and now I've got 2 non-bonding pairs of electrons. So 5 electron domains. It's 5, that means that the electron domain geometry is trigonal bipyramidal. So where are those non-bonding pairs of electrons going to go? I've already given the West, it's on the equatorial position. Here's my central chlorine. There are my fluorines. I left off some electrons in this Lewis structure. So let me go back and throw those in. So I put them in here. And now, here are my, don't let these think these lines as being bonds. But I'm trying to show where those equatorial positions are. So if that's the case, there's my third fluorine. And then there, on the equatorial positions, are my other domains, my 2 non-bonding domains. So these are both in equatorial positions. And so here's what was my seesaw a moment ago. This next non-bonding pair has to come off an equatorial position. So there are my axial atoms. There are my axial atoms. That's my atom on the equatorial position. And there's one non-bonding pair, and there would be the other non-bonding pair. And so that gives us a T-shaped molecular geometry. So that bond angle, ideally, would be 90 degrees. It's actually going to wind up being a little bit less than 90 degrees because those non-bonding pairs of electrons have greater repulsive forces than do the bonding ones. And so the true bond angle is going to be a little bit less than 90 degrees. It's going to vary from molecule to molecule depending on the atoms. Didn't mention bond angles back in the SF4. There's the bond angle between the axial and equatorial positions. Ideally, that's 190 degrees. 120 degrees between the fluorines, but actually it's going to be smaller than that. The actual bond angles, because that non-bonding pair of electrons has greater repulsive forces. So there's one more case of looking at 5 electron domains, and that's going to be in this ion, IF2 minus. In which there are actually 3 non-bonding pairs around the central iodine, plus 2 single bonds, each worth a single electron domain. So we've got 5 electron domains once again. That means my electron domain geometry is trigonal bipyramidal. And where do those non-bonding pairs go? They go on the equatorial position. So I'll redraw that. There's my axial positions. And so my bond angle, so this, my actual bond angle, my molecular geometry, it's linear. It's 180 degrees. Remember, in the molecular geometry, yes, we're influenced by the non-bonding pairs, but all we are looking at are the positions of the atoms relative to one another. In this instance, it's linear and 180 degrees. Let's talk about 6 electron domain molecules. An example of this would be sulfur hexafluoride. So that's the correct Lewis structure. Sulfur does not obey the octet rule. It actually has an expanded octet, and there are 12 electrons around it. And what this is going to, so the electron domain geometry is going to be octahedral. Now we've made an octahedron. So this is an octahedral. And so here's my octahedron. And in it, all the bond angles wind up being right angles. They're all 90 degrees. And so you might think of it as being two square pyramids that are base to base, not face to face, but base to base. And so there's my octahedron. And so there are no non-bonding pairs of electrons on this molecule. And so it also has a molecular geometry being octahedral. There's another way we can have an octahedron, and that would be for a molecule like BrF5. Bromine with 5 fluorines and a non-bonding pair of electrons. So there are 6 domains, because there are 5 single bonds and a non-bonding pair on the bromine. So 6 electron domains means we've got an octahedral electron domain geometry. So the question becomes, where is that non-bonding pair? So all positions are equivalent. Now in the trigonal pyramid situation, they weren't all equivalent because the bond angles were different. There were 90-degree bond angles, 120-degree angles. Here they're all 90, so they're all equivalent. And so I can pull it off at any one position. And so what I've made is a square pyramid. So you see the square, and then if I turn it this way and maybe use your virtual reality minds, you see that there's a 4-sided pyramid, and down here's the base. So the molecular geometry, the shape is that it's a square pyramid, or it's a square pyramidal shape. The geometric figure is a square pyramid. The shape is a square pyramidal shape. And last but not least is xenon tetrafluoride. Xenon with 4 fluorines and 2 non-bonding pairs of electrons. So I got my 4 single bonds, that's 4 domains. I've got 2 pairs of non-bonding electrons, so that gives me 6. So the electron geometry is octahedral. And so we go back to my square pyramid that I had a moment ago. So where is this other non-bonding pair of electrons going to reside? Is it going to come off down here, or will it come off on the opposite side of where that non-bonding pair of electrons is? And remember, trying to minimize the repulsive forces. So by having those non-bonding pairs be on opposite sides, maybe if I add these in, it might help you see a little bit better. Let those be non-bonding pairs of electrons. That minimizes the repulsive forces between those non-bonding pairs. It also makes the molecule more symmetrical. Remember, nature loves symmetry. So those are my non-bonding pairs. If I get rid of those, now I've got a molecular geometry or shape of being square, planar. And all 5 of those atoms now are found in the same plane.